Hey everyone, welcome back. Today I'm going to be discussing walk-forward optimization and how to code it using Python, VectorBT, and Alpaca market data. So let's get started with a definition of walk-forward optimization. I have the good old Wikipedia page open right here. It says it's a method used in finance to determine the optimal parameters for a trading strategy. Walk-forward analysis does optimization on a trading set, tests on a period after the set, and then rolls it all forward and repeats the process. So that way we have multiple out-of-sample periods and look at all these results combined. This was originally discussed by Robert Pardo, and it says with walk-forward analysis, it's less likely to suffer from overfitting. So what does that mean? So in my first video on VectorBT, we went over this example. We downloaded a historical data set, and then we generated a range of windows. And what you can do with VectorBT is it has this run combinations function. And so rather than just passing in one set of parameters, so the 10-day fast-moving average and the 50-day slow-moving average, and running that, you can pass in a whole range of them. So from 2 to 101, you can run every single possible permutation of this all at once, and then it can return all the results. And you might want to say, hey, optimize this and return me the best pair, like which combination of parameters here had the best total return, right? And that might sound good at all at first glance. You might think, oh, let's just find the best possible outcome. What you'll probably find is when you take these optimal parameters that you've tested on historical data and then try to trade them in the future on data that your model hasn't seen yet, you'll probably end up losing money or underperforming. And we'll demonstrate that with code in a moment. But before we dive into the code, let's discuss this conceptually. Why is this particular example likely to lose us money? We're downloading historical data, we're testing our strategy on historical data, we're finding the absolute best one, and then we're selecting it and then trading in the future. Why is that not going to work? The problem, as you may have guessed, is overfitting, and a solution to this is presented in Robert Pardo's book, Design, Testing, and Optimization of Trading Systems, which is referenced in the Wikipedia article. This book is written in 1992, so some of it is probably outdated at this point, but I do have a copy of it here, and I'm going to highlight a few of the specific sections that describe this process of walk-forward optimization and how it presents a possible solution to overfitting. So this is chapter 7 of this book. It's titled Optimizing the Trading System, and I've highlighted a few key points here. There's a section here on optimization. So he says, in this book, optimization means parameter selection. The goal of optimization is find the values for model parameters that will generate peak trading performance in real time. And so isn't that what we did, right? We found the optimal parameters that we selected when we ran all the different combinations. No, he says what actually happens is inadvertently, such user trading software think the optimization result showing the biggest profit is one and the same as the one that will generate peak real-time performance. And he says if the model has not been walk-forward tested, there can be little confidence in its real-time trading ability. He goes on to say that optimization can rapidly degenerate into what is commonly referred to as curve fitting. It is common knowledge among statistical modelers that given enough variables, a curve can be made to fit any number of data points. Because a curve produced by modeling procedures fits past data quite closely, it's no guarantee it will be a good predictor of future movement. Closeness of fit does not imply the best predictive power. In our work, it is often just the opposite. So he goes on later in the chapter to discuss the technique of walk-forward optimization. He says it has 2 steps. Trading models first optimize on a piece of history, then is traded on a new piece of history. So at the end of the chapter, he does an actual walk-forward analysis by a software trading system called Blast. As I mentioned, this book's like 30 years old, so I don't know if Blast exists anymore, but he gives some helpful details on how to set this up. So he does S&P futures for a historical period from 82 to 1990. So for convenience, let's just call this a 10-year period. And what he does is divide this up into a window size of 4-year chunks, but he doesn't go like 4-4. What he does is do like a rolling window, so it's like 4 years, and then he has a step window size. So he advance it forward 6 months, gets another 4-year period, advance it forward 4 years, and then advance it forward 6 more months. And of each of those 4-year chunks, he divides that up into like a 75%, 25% training and testing split. And so for that 4-year period, you might want to optimize on the first 75% of data, and then you test that out on the next 25% of data. So I think the best way for me to explain this is to write some actual Python code and show this visually. So that's what we're going to do now. So what I've done here is download 5 years of historical market data from Alpaca for the S&P 500. This is just daily data from January 2016 through the end of 2021 here. So 5 years here. And what I did was take VectorBT and try to optimize a moving average strategy to find out the best possible results for this particular time period. And if I show you this on TradingView, what it looks like is, look at this. I am really good, right? So you can see how I have a buy signal here where this green line is. I capture this uptrend, I sell, I capture this uptrend, there's my buy signal there, capture all of that, and then I sell again. I short right here, I buy, sell again, I short right here, and then buy, sell again, and so forth. And you see these green periods, I'm just riding this uptrend the entire time, and then selling right here, and everything is beautiful, right? I've run this perfect back test, and I've perfectly predicted this 5-year period. I've perfectly predicted the past, and that's because I've optimized my moving average strategy to match this exact period of time, so it just looks really good. And you'll see all these back tests like this on TradingView, and they paint a very pretty picture, but what I'll demonstrate in a moment is whenever I try to trade this strategy into the future, in the year 2022, you'll see where it starts to fall apart. And so the solution presented by Robert Pardo is this walk forward analysis. And what it does is divide this entire segment of time into a bunch of different chunks that we test on. So rather than fitting to this entire period, which might include very specific events like COVID right there, you want to divide this up into a bunch of different market regimes. So the visualization of walk forward analysis looks like this. This is described in this Jupyter notebook. So if you look in VectorBT's GitHub repository, there's actually a Jupyter notebook that goes over a lot of this, but you see it's just code here, so there's no real description of what's happening here. And I thought it'd be useful to break this down and describe it a bit more. That way we can see exactly what's going on and understand it a little bit better step by step. So what I did here is split this 5-year period into 360-day chunks. So this is 360 days from the beginning of this blue to the end of this orange. And then I went forward a little bit. This is 360 days as well, forward a bit, then 360 days. And we have 20 different unique periods to test here. So what we can do is take each of these 360-day periods and split it up into a 70% optimization testing set and a 30% out of sample set, okay? So you see here I have it coded and it says in sample is blue, out of sample is orange. And so for this first 70% of data, what we do is we can do that run combinations and optimize for this first 70% here. And so this will be our training set, our in sample set, right? And we find out the best possible results for this particular chunk. And so what we can do is take the parameters we find in this first 70% of data and then run it against this orange set here, so this other 30%, which our model has not yet seen yet. And we'll simulate taking a back test here and then live trading it against this 30% here. And we already know the results of this, but our model doesn't know the results. And then we can validate, did this optimization here result in good results whenever we test it using this out of sample data. After that, we can go to the next chunk here. We can optimize for this segment of time, which has its own unique characteristics, and then test it against this orange period, right? And then we keep doing that and so on and so forth. We optimize against each of these test samples, and then we roll it forward, and then we test against this out of sample data here all the way across. And then you can see we've actually tested our system against a variety of time periods. And also we have all these different out of sample tests where we quote live traded it and we're able to validate a little bit. And then by the time we get to the very end here to the present day, we're feeling a little bit more confident that we've tested our strategy in a variety of market conditions. And not only have we tested it with historical data, but we've live traded it in a bunch of different time periods as well. And we've already seen some results of our strategy reacting to some conditions it hasn't quite seen yet, so we're feeling a little bit more confident. So hopefully this description and visualization of walk forward analysis has given you a little bit better understanding of what walk forward optimization actually is. Now let's go ahead and write some Python code to download this historical data set and split it up into chunks and create this visualization and run some of these optimizations so that you have a grasp on how to do this in code. Let's go ahead and get started. All right, so the first thing is we need to set up our project. So I'm using Visual Studio Code, and I'm going to create a new file. I'm going to call it walkforward.py in a new directory, and we need to install some packages. So we're using VectorBT, so we'll need to install that. I'm going to put all the different packages we need in a file called requirements.txt, and I have this written down somewhere. Okay, so we need VectorBT. And we need to make sure we get the latest version because there's been some changes recently. There's been a lot of upgrades and bug fixes since the last time I discussed VectorBT. And so I just revisited it, and we have 0.23.2 is the latest version. We also need NumPy, and I'm specifying a specific version in the requirements.txt here because I got an error if I didn't have a certain version. I also want to use Alpaca Trade API. Because I want to use Alpaca to fetch data. And there's a library called Kaleido I need for some reason when I was trying to do the visualization with VectorBT. So I'm installing that as well. So I'm gonna do pip3 install-r requirements text, and I'll take all those packages in this file and install those versions of it and make sure it all works properly together. So I'm gonna install all of those packages. So one thing I want to note is if you've installed VectorBT before, I'm going to run the Python interpreter real quick, and I'm going to import VectorBT. Make sure you have the latest version. So you notice I put 0.23.2. So if I import VectorBT like that, and I type VectorBT underscore version like that, it's 0.23.2. If you have 0.21 or something, make sure you upgrade to the latest version. So the first thing we're going to need to do is to download some historical market data. As you know, there's a variety of places you can get your market data from, and in VectorBT here, there's some custom data classes that you can use, and these are the different sources you can use. You can use Alpaca, Binance, CCXT, synthetic data, and Yahoo Finance data. As you may have guessed, I'll be using Alpaca for market data for a few reasons. Number one, Alpaca is a sponsor of the channel, so I'll leave a link below if you want to sign up for Alpaca. It really helps support the channel. Number two, Alpaca provides an ordering API. So if you're making an application like this, chances are you don't just want the historical data. Eventually, you actually want to place a trade. So not only does Alpaca provide a way to download market data, you can actually execute real stock and crypto trades, use a news API, and a bunch of other services they provide. Number three, if you use Yahoo Finance, it is free. However, a Yahoo Finance API isn't really an official API. You're essentially screen scraping Yahoo Finance. The structure of the page can change. It goes down sometimes. So the library kind of is a little bit flaky at times. And with Alpaca, you have a developer first company. So their entire business model is reliant on having a reliable API. So you can go there and actually get support. They have a community of 12,000 Slack members if you want to talk to people about the API. So how do you actually use this thing? So if you go to the VectorBT page and scroll down, I tried this out. It turns out this isn't quite accurate. So I don't know if their documentation is out of date, but if you go to Alpaca's website, Rahul here, who I actually had the pleasure of meeting, has written an introductory article on backtesting with VectorBT. And so I looked at how he did it right here. So I'm going to borrow his API key setup right here, and then I'm going to make some modifications and add on to it. So he imported VectorBT. We have that installed already. And you just need to set up your key ID and secret key. And I'm logged into my Alpaca account right now. So I'm logged into Alpaca right here. This is the paper trading side. I can switch over to my live trading account if I want to place real trades, but this is where I test all of my different programs. So on the right here, I can generate my API keys. So this is API keys here. I can hide that, I can show, I can regenerate a new key, and I'm just gonna take this key, and I can show it to you because I can just throw them away over and over again. So I make a new one for each video. So I don't care if you see this or not. So there's my API key and secret key. You can put it in an environment variable, or you can put it in a config file if you don't want to put it in this main file. It's better practice to keep it separated. So that's set up now. And so let's see how he gets the data here. So he's able to get a pandas data frame. So one nice thing about this Alpaca data download here, you get one line here and you do get data and you get this pandas data frame, and we can start operating on it. So I'm going to take this as well. I don't need this little bit. I just need the data here. And so I'm going to do data equals vbt.alpaca data download. And I want to get a SPY here. And what I want to do is, I don't want to start 4 days ago. I want 5 years of data. And so I want to go back to 2016. So I'm going to do 2016-01-01 like that. And then the end here, I'm going to do, what did I say? I think 2021, and the end is I'm going to use December 15th here for a specific reason. I'll show you why in a second. And I'm not going to get hourly data. I can do daily data. And this market data lets you get data by the minute time frame, the hourly time frame, or the daily. So that's all good. That's all there. And then now I can get the data. So I'll say data equals alpaca.getData. I'll do it like that. And then I'm going to print data and see what that looks like to see if this is working. Okay, so I'll run that. and it says Alpaca data has no attribute download. And I think this is actually supposed to be lowercase, so that's one thing to change. So I'm going to do a lowercase download right there. Missing one required positional argument symbols. And then I think I need to change this positional parameter as well. I think there's been a couple of changes since then. So .download positional argument symbols. So in the first position, what I'm going to do is put spy like that. And then I think I can just do data here actually instead of alpaca.getData. And so what I'm going to do is just get data like that. Let me see if this works. So data equals vbt.alpacadata.download and get 5 years of data start to end here on a certain time frame. All right, and so it looks like I got something, and now it has a pandas data frame. And so what I actually need to do is data.get. So if I run data.get here, what it does is give me the actual data frame. And so you can see from 2016 through 2017 here, I have open, high, low, close volume data on the daily time frame. And so why do I only have through 2017? It says 500 rows and 5 columns. And so what we actually want to do, I think by default, it gives you 500 rows of data. And so what we want to do is do a limit here. So by default, it'll just give us 500 just to save resources. And if you really want more data, you can just do a big limit there. So I'm going to do limit equals 10,000. Let's see if that works. And you can see now it goes all the way through December 15th, 2021. And the reason I stopped at December 15th, 2021 and got this exact time frame is you can see now there's 1,500 rows, right? And then I said I wanted to divide up this data into a certain number of chunks, right? So what I like about this 1,500 number is that I wanted 5 years of data, but I stopped a little early because 1,500 seems kind of nice and evenly divisible if I want to divide this up into even chunks, okay? So the next thing we want to do is we don't really want to, since we're just operating on price here, we're just going to get the close. So I can, instead of just .get, I can just do .close right like that. And then this will just get me a series of the closing price for each of the dates, just like this. And I'm going to run that, and you see I have dates and I have closing prices for 5 years. So this is exactly what I want. And so now I can go ahead and plot this data. And so with VectorBT, I can create a new figure here. And so I'm going to do since I have data.close here, I'll just assign that to a variable called price. So price equals data.getClose, and I can do price.vbt.plot. So this is all in the VectorBT documentation if you search around under plotting, but if you just want to copy what I'm doing, it's price.vbt.plot, and then I can give it some names. So I can do trace names equals price, and I'm just giving it a width, and so just making it 1280 and a height of 720 personally is what I'm doing. And then I'm going to do figure.show just like that. So you have this object, so you're plotting the price and you can show this figure. And this will pop up in a browser. And you can see here's my 5 years of data downloaded from Alpaca, and I got the closing prices, just plotted it on a regular old plot. So far so good. So that was just to visualize what we have. So I'm just going to comment that out for now, and we're going to continue on. So the next thing we want to do is talk about those combinations. So remember we said we can optimize our strategy or optimize for particular parameter values. And so what we can do is we can import a NumPy. So I'll import a NumPy, and I can import pandas, right? And then so what we can do is do that whole run combinations thing. So I'm going to do Windows equals numpy dot arange 1050, and so this will get all the different combinations between 10 and 50, and then we can do fastma slowma equals vectorbt.ma.run combinations. And this is all in the documentation and examples. That's where I'm getting this from. And then so I can do run the combinations on my price. I pass it the window, so the different combinations. So we're running all these different window combinations for moving averages on price here, right? And so then we get our entries and exits. So we have fast MA, and then we have MA crossed above the slow MA, and then we're exiting when the fast MA goes below, crossed below slow MA, right? Okay, and then we do vector portfolio equals vbt.portfolio. And this was all in the very first video. I know it's been a long time, but this is where I'm getting this from. It's all in the first video. I went over all this stuff on VectorBT. And so we pass it price and our entry and exit list here. And then we're giving it a frequency of 1 day. and then we can say which direction. If we want to just go long only, we're going to do direction equals both, so that it does long and short. So I'm doing direction equals both here. All right, looks like we have some object with a bunch of values. So let's go ahead and run one of the functions. So when you have this object here, there's a variety of functions you can run on it to analyze the portfolio results. So I can do total return, I can do max drawdown, and so forth. So I'm going to print the total return here. And look at that, we have all these different window combinations. So 10 and 11, this is the total return, and then it goes all the way down to the 48 and 49 windows here. So we have a bunch of different permutations. So what we can do is we can print all the returns, or we can also do sort values here, and this will sort by total return. And then we can get the window combination that had the highest total return. And you'll see this is actually going to be overfit. So if you go down here, you see this is the highest total return. You can see there's this 32-day fast moving average and 43-day slow moving average. And so what I did earlier is I got TradingView for this moving average cross strategy, and we can type in those numbers, 32 and 43, or 32 and 41, and you see when I do it here and type that in, you can see it plots it all nice and beautiful, but you can see how closely it just kind of traces what's there in order to produce those results. And so we have this back test that looks good and it has good returns. You're dodging all these drawdowns. So during COVID, oh, what do you know? You sold and went short right there, which is great. You captured all this, and then you went long, right? But as we can kind of intuitively see now, this is very overfit. And if we projected this into the future and started trading it, the future is not going to look just like this, right? We need something that's a little bit more adaptable to different market conditions. So how do we do the walk forward optimization on this? Well, before we do that, let's go ahead and prove that these two parameters won't produce good returns in the future. And how are we going to do that? Well, you remember that I downloaded data from 2016 through the end of 2021. It's actually March of 2022 right now, so actually there's some future that this thing has not seen yet. And so let's go ahead and get some more recent data using this Alpaca data download. And so I'm going to go down here to the bottom. We can get new data, so future data. Let's just call this future data. And then let's just get this from 2021. And we'll get a little bit that's already passed just to make sure there's some trades. Since this is 30 and 40 days, we need to make sure we have enough data. And then so we'll do that through the present. So we'll leave it with no end. That way it goes till the present. And yeah, so that should get the future data that we can test this on. And we can do the same thing we did earlier and actually run fast MA and slow MA on it. So I can do fast MA equals VBT.MA.run future data. And then let's just do the 30 and the 40, right? So we have all these ones around 30 and 40 here. And so we can just run it. The fast MA is 30 and the slow MA equals VBT.MA.run future data and 40. So that's our fast and slow. And then we can do entries equals fast MA, MA crossed above, slow MA, and then exits equal fast MA.MA crossed below slow MA, okay? Okay, and then we can just go ahead again and do this portfolio equals VBT.portfolio from signals, and I'll go ahead and copy it up here since that's a little faster. Portfolio from signals, instead of price, we're gonna do future data. We have our entries and exits. We have a 1 day frequency, right? And then we can go ahead and print a portfolio total return and see what that returns if we run these optimized parameters on this latest data. Okay, so I'm gonna do that, run it and see what our total return is. And I got an error here, and that's because I got the data, but I didn't get the close. So let me do .get close, just like that, so that we get the close in future data. Okay, so I'm gonna run that again. And you see we have a -4% return, -4.6% return. Unfortunately, our beautiful 30, 40-day thing didn't work very well on this data that it hadn't seen, and so we got to go back to the drawing board. So how do we actually divide this data up into chunks the way we do it with walk-forward analysis? Well, there's a VectorBT notebook here that shows you an example of how to do it. Like I mentioned, there's not much description of what all this does, but what it shows you is this roll in and out samples. So there's this rolling split here, which has some keyword arguments. And if you scroll to the top, you can see where he has some keyword arguments documented here. So you kind of have to look at this and figure out what's going on. And so I extracted a lot of this out to kind of explain this. And so I'm going to show you that here. So what we can do is I'm going to comment this part out since that just was to prove a point, this whole future data thing. But what we have up here is this portfolio, entries and exits and run combinations. I can comment that out as well. And so right now, let's just start where we have the price. We have the closing price for those 5 years. And what I want to do is divide that up into pieces. And so if you look at how this is done, there's some keyword arguments with n equals 30, a window length, and set lengths, left to right equals false. Okay, so this says 30 windows, each 2 years long, reserve 180 for test. And so what I did was extract this out. So at the bottom here, I'm going to say price.vbt.rolling split. So the function is called rolling split. So if you go to VectorBT rolling split, look that up, you see there's this rolling splitter. Splitters right here, and this shows about how to split range into sets. Okay, if you want to read the details here, and then it shows set length, so the length of the training set and the length of the test set. Okay, and so let's type this in. So we have a rolling split, and so I need to say the number of chunks I want to split into. So I want 20, n equals 20. Window length, I want that to be 360, I decided, and so that's 360 trading days. And I want to split that between a test set, an in-sample set, and an out-of-sample set. So we're going to optimize on the in-sample set and then reserve some out-of-sample data so that we can live trade against the out-of-sample set, right? And so what's 70% of 360? Well, that's 252. And so I like that number, right? The reason I chose 360, 70% of that is 252, and there's about 252 trading days in a year. And then so I'm going to use that. And then so that means I'm going to reserve for my out-of-sample set 108 days. So 360 minus 252 is 108. And so in their documentation, the way this is done, we do set lengths equals 108 comma. So it's a tuple like that. So it's just a tuple of 1. And then this left to right parameter determines which side of that split is the test side and the test side. The test side and the training side, okay? So the default is true, I think, so we want left to right equals false, okay? And the first thing I want to do is actually plot this, so you can actually pass a plot equals true, and I think we're good there, so that's the figure. So this will actually return a figure if we do plot equals true, and then we can do figure.show. And let me see if this works. So I'm going to run this rolling split. It should divide it up into 20 chunks of 360 days rolled forward. And look at that. So we have that. So we have 20 chunks, 1, 2, 3, 4, all the way to 20. And you can see how they're distributed through this 5-year range. So we have exactly what we want here. And we can update this and make it bigger if we would want to. And so if we did that, all we have to do is do figure.update layout width equals 1280, and then height equals 720. So that's not required, but it's easier to see now. So you can see these 20 chunks here and how they're distributed. And so now all we need to do is just let's look at how this splitter works here. So let's break this down a little bit more. So I'm going to comment out the figure part here. So we don't need this figure anymore. So I'll comment that out, and then let's go ahead and get this rolling split bit. And instead of doing plot equals true, we can just take that off. So if we take the plotting off, it'll actually return a tuple of values. And so the way this looks is it actually returns 2 tuples here. So it's going to run rolling split, and it's going to return in-sample prices, in-sample dates, and out-of-sample prices and out-of-sample dates. So let me make variables. So what I'm doing is doing an assignment here. So I'm doing in-sample prices, comma, in-sample dates equals Actually, what I should do, let me go ahead and show you what this looks like. So let me just assign this to D here. Trying to really break this down even more. So I'm going to print that out so you see how the data actually comes back and why I'm assigning it to multiple variables. Okay, so you can see all these different series of dates returned. So there's July 15th through, looks like December 15th. There's April 20th through September 21st. And there's a bunch of chunks getting returned here. And then you can also see a bunch of different prices here. And so this is all in just one big blob of data. Let's break this up a little bit more. So instead of just printing this whole thing, that's why I'm getting this tuple and unpacking this. So I'm doing in sample prices, comma, in sample dates, and then comma, out sample prices, out sample dates here. Okay. And so that's how it's returned. And so now let me show you what the in sample dates look like. So I'll print int sample dates. And when I do this, you should just see one set of dates. So it'll show all of these different blue boxes here, right? So at the very beginning of in sample dates, you see the first one starts at January of 2016, goes all the way till the end of 2016. So that's the 252 trading days I mentioned. And then there's a new set. It shifts over by a few months. And then you have March 31st all the way through March 29th of the next year, shifts over by a few months, June 24th, all the way till June 23rd of the following year, and so forth, right? And so if I print the out of sample dates, as you can guess, so if I print the out of sample dates, do that, you should just see a shorter bit of out of sample dates. So you can see the last 6 months here that you would test on. So that'd be July 15th of 2021 through December 15th of 2021. And so you see these short test period sets. So this is 30% of each chunk all in a row like this. And then we can print the prices, right? Out sample prices. So we have the indexes, and then we have the closing prices associated with those indexes. So if I print the out sample prices here, you see all the indexes we have all in a row, and then so you can see all of those lined up. And so if I do out sample prices 19, since we have 20 chunks, this will be the last set of out sample prices. Okay, so if I do that, you see the 108 days. Remember, we had 252 in the in sample set and then 108 in the out of sample test, right? And so this is the last chunk, and this is the last 108 closing prices of the year up until December 21st. So 0 through 107, you include 0, and that's 108. So jumping back to the VectorBT notebook here and zooming in, you can see he does a simulate all pairs for in-sample ranges. So we have our in-sample prices, and so he has a function called simulate all params, and it just accepts price and windows. So we have a price, we have our windows already. And so all he's really doing is running the combinations on the in-sample prices. So we're optimizing on each of the in-sample prices. So it's just the same thing, the MA cross above and below, and he's getting the Sharpe ratio of each one. So that's one thing we can do as well. So we can get our in-sample prices. So let's get this run combinations here for the moving averages and our from signals and total return. And let's go ahead and grab this up here, and let's move this down to the bottom. And what we can do is just run this on our in-sample prices. Okay, so comment this out. Okay, so we have our windows there, and instead of price, we'll just run it on the in-sample prices. Okay, we have our windows, we have our entries and exits, and then we need our in-sample prices, exits, entries and exits. And then we can get the Sharpe ratio like that. And let's see what that looks like. So I'll run that. So look at that. So now not only do you have these different moving average windows, you have the results of them optimized on each one of the in-sample splits from 0 through 20. And so what he does next, he actually does this get best index, and he just groups them by the split index. So I can take this from here, and then let's just have the portfolio. So I'll do Sharpe ratio equals portfolio.Sharpe ratio, and then I can just do a Sharpe ratio, and then actually let's do what he did. Let's just call it performance equals Sharpe portfolio.Sharpe ratio, and we're going to group by index and get the maximum one, and I'll print that out. and delete that. So look at that now. So we have 20 different sets of in-sample prices. So 0 through 19, we ran the Sharpe ratio on all of the in-sample price sets, right? And so now when it comes back, we're grouping by the index and finding the maximum. So now we have the best set of parameters for each of those in-sample price sets. And so we don't necessarily have to sort by the best one here or do the Sharpe ratio. We can do a max drawdown, for instance. So we can do performance equals portfolio max drawdown, and then we can sort again as well to find different parameters. We can do a total return and any of the other functions that are available to analyze a portfolio. We don't have to take the best one for any particular one of these. We can look at all the different parameter values that perform the best for each thing we're trying to optimize, and then select a certain set of parameters that we feel good about, and we can run that against all these different outsample prices we have. So we already have these outsample dates and we have outsample prices. So we can take our different parameters that we've calculated based on the insample dates, run them on the outsample dates, see how they perform, and if a set of parameters has met our performance requirements and works well on the insample dates and then performs well on the outsample dates that it hasn't yet seen, then we can feel more confident that we can use those parameters that we select when we bring the system live. So that's pretty much it. I'm not going to show you any particular parameters to use. There's no financial advice in this video. It's just a programming video that shows you how to analyze the data. Those decisions are up to you. I just wanted to talk to you about how to do walk forward analysis, and hopefully this video was helpful in describing that and giving you some type of process to do this parameter selection. So thanks a lot for watching, and stay tuned for the next video. Thanks.